welcome everybody to today's STEMPS webinar. So today we are very happy to have Mark Risser as our speaker. So Mark is a research scientist at the Lawrence Berkeley National Laboratory, where he's with the Climate and Ecosystem Sciences Division. He also a PhD in statistics from Ohio State University, which he obtained in 2015. And since then, he has been at Berkeley Lab. His research interest is in using data science, Bayesian statistics, and computational tools for identifying and quantifying climate change. He has special interest, for example, in statistical climatology, extreme value analysis, Gaussian processes, and Bayesian modeling. Recently, he has, for example, been working on statistical methods for detection and attribution of climate change. And that will be the topic of his talk today. So his title is Detecting Multiple Anthropogenic Forcing Agents for Attribution of Regional Precipitation Change. With that, Mark, please go ahead.
Okay. Well, thank you, Mikhail, very much for the introduction. It's a real, and also to you and the other members of the organizing committee, it's a real honor to be presenting in this seminar series. So yes, as Mikhail said, I'm a research scientist at Berkeley National Lab. I'll be presenting some of the recent work we've done over the last few years with a quite large list of collaborators. I guess I'm now realizing none of whom I've listed here. And then also to acknowledge that the support for this work has come from the U.S. Department of Energy Regional and Global Model Analysis Program. I think there should be plenty of time for questions at the end. So, but I'm also more than happy to, if there are questions throughout, for folks to interrupt. I'm not sure I'll be watching the chat, but maybe Mikhail or Alex can help me keep an eye on that. Okay, well let's go ahead and jump in. I'd like to start out a talk with kind of the key takeaways. What's the ultimate message that I hope to communicate with you today? So the first thing, the objective here is to kind of break down how human-induced factors, things like greenhouse gas emissions and aerosol emissions, influence heavy rainfall events, focused on here on the continental United States. And the first kind of major thing that we find is that greenhouse gas emissions lead to increases in rainfall extremes. Aerosols kind of have a mixed bag response, and on the longer term, they tend to lead to drying or reductions in extreme rainfall. But then on the shorter term, the impact can be quite different across different parts of the year. And our results also show that as aerosol emissions locally here in the US decrease, as they have been doing quite rapidly over the last 50 to 70 years, this long-term drying effect is going to be going away, which might cause these rainfall extremes to increase much more quickly than we would have otherwise expected. So those are kind of the headline messages. I'll try to communicate those over the next 30, 40 minutes here. Okay, so kind of jumping right into some motivation. The two primary topics for today's talk are detection and attribution of anthropogenic climate change. And second, from a methodological standpoint, the extreme value theory or extreme value analysis for measurements of extreme precipitation. So I want to give just a little bit of a background on each of these topics, just to make sure we're all on the same page. Okay, first, detection and attribution of anthropogenic climate change, or simply D&A. As the name implies, this is a two-part exercise where, for a given climate variable of interest, whatever that might be, temperature, precipitation, surface pressure, whatever, the first thing you do is to try to see if you can detect some systematic change in its distribution. Usually this is a change over time, but it could be more general than that. The second part of this is then, assuming you have been able to detect a systematic change, is that you try to attribute that change to a specific human activity. So it kind of playing the cause and effect game. So yeah, at its core, detection and attribution, you can kind of think this is in the statistical world, this would be referred to as causal inference. Specifically with climate change, DNA is looking to make cause and effect statements about if, how, and why, different aspects of the global climate system have changed or are changing due to human-induced factors. And by now there's many decades of really important results out there in this field. A lot of very conclusive evidence for human influence on different aspects of the Earth system, things like surface air temperature, sea level pressure, and a number of other things. But it is still an active area of research. There's other climate variables on certain spatial scales, extreme events, a lot of areas where there's still inconclusive evidence or a need for new methodology, and that's kind of what we're getting at today. So take a quick detour now into extreme value analysis. So I'm going to keep this at a very high level, but just to kind of orient us all here, if you go back to your Stat 101 course, or what I would call, I guess, ordinary statistics, if we have a distribution, what we're interested in a typical sense is the average or the mean of the distribution. So we kind of want to know what's happening down here in the bulk, or where most of the measurements are. Extreme value analysis, this is the study of rare events. This is instead trying to characterize the tail of the distribution. So kind of on this far right side of the plot, we want to know about those values, what their magnitudes are, what their probabilities, et cetera. And as you can probably imagine, this is really important in a lot of different places. Obviously the insurance industry or risk assessment really cares about the rare events. In an engineering context, obviously this is also important for, what's the sort of worst case scenario that can happen if I'm designing some new infrastructure. And then, more relevant to the topic today that I'm speaking on is for weather. We also are interested in things like heavy rainfall, heat waves, hurricanes, lots of other rare events that are really important. And when we talk, so I'm going to be focusing in then on extreme precipitation. Again, just to make sure the terminology is clear, precipitation can refer to either rainfall, the liquid form of precipitation, or snowfall, solid precipitation. And by extreme precipitation, I'm just talking about periods of heavy rainfall or snowfall that are much larger than what you would get on a typical day. And again, in the purpose of this talk, I'm going to be looking at sort of daily precipitation extremes. So kind of the accumulations over 24 hours that are unusual. And why do we care about these? I think kind of clear, but just to give a couple examples, these are usually, again, the most costly societal damages, things that happen. Hurricane Harvey was an example from a few years ago now, where the hurricane hit the city of Houston and led to a lot of rainfall fell and led to really serious flooding and lots of damages associated with that. More recently, if we go to the Northeast last summer, there was lots of flooding, and again, other parts of the world. I know last year was kind of a bad year for that as well in parts of Asia and other places. So heavy precipitation, extreme precipitation can be a problem. Extreme precipitation can also be a good thing. About a year ago, there was a series of storms in January that in California that lifted the state essentially all at once out of drought conditions over the series of a couple weeks. So it's I guess what I'm hoping to communicate here is that it's really important to understand how these extremes, understanding them, but also how they're changing from a sort of planning and management standpoint when we're talking about human systems here. Okay, so let me go back to say a little bit more about detection and attribution at a kind of high level. The detection and attribution is definitely a data-driven field. We use different types of climate data to result in detection and attribution conclusions. The first type of data that usually gets fed into these sorts of analyses are what we would call observations. And again, observations can mean a lot of things, but for the purpose of this talk, I'm going to refer this to sort of direct measurements of nature that are collected at monitoring stations. And globally, or I guess even locally here in the U.S., there's quite a few even monitoring networks that are out there. One that I use quite a bit that's really nice is the Global Historical Climate Network. This is a open source database that has daily measurements from land surface stations from all over the world. Again, quite a few records included in that database. Again, I'm going to focus in on the United States. We wanted to kind of look at these more local scales, regional scales relative to global. This is a especially good network because in the United States, there's quite a few stations that have records that extend back to the beginning of the 20th century. So we have 120 or so years of pretty high quality data that, the spatial distribution of which is shown there. But anyway, observations are a critical ingredient to detection and attribution studies. The other, in a traditional sense, the other key ingredient here are dynamical models, which again are just physical numerical representations of, in most cases, the globe, but you can also look at these more regionally. And just as a little toy schematic over here, how these models work. They're a computer model, but then they divide the globe up into a bunch of little grid boxes, horizontal and vertical. And then these sort of simulate what the Earth's climate might look like, including sort of our physical understanding of the Earth system. Also, oftentimes within these grid boxes, there's models or parameterizations for how things are changing or evolving. But these global climate models that kind of simulate the entire globe are, again, another main really important tool for detection and attribution. They do tend to have fairly coarse horizontal resolution. Sort of CMIP6 class anyway is still about 1 degree or 100 kilometer square grid boxes. So that they can't resolve that many things at a global scale, but useful nonetheless. And again, you could think about these as really a test bed for climate scientists to understand how the Earth system might respond to different versions of reality, hypothetical versions of reality. The model could be set up to simulate our climate in a world without humans, or kind of what might happen in the future, or maybe somewhere in between. If we want to isolate a specific human influence, we could turn some of those on, turn some of those off, and kind of play that out to see what happens. So again, a really useful and important tool for that climate scientists use to kind of understand past and future climate. However, kind of coming back to why are we studying this, detection and attribution for extreme precipitation? At the moment, this figure that I'm showing here comes from the most recent Intergovernmental Panel on Climate Change, their 6th assessment report. At the moment, there's actually quite low confidence in the human influence on extreme precipitation, especially if we're talking about North America here. So this figure, what it's showing is, you can kind of imagine this takes all the land areas in the globe and pixelates them up. So North America is up here in the top left. The color of the box indicates the type of change, sort of as synthesized over all our best state of knowledge here. The type of change are extreme precipitation events increasing or decreasing. And then the dots and I guess hatching here kind of summarizes the level of confidence. So first, it's important to note that you have all green colors here. So in general, human influence is causing precipitation extremes to increase. But when we look at individual boxes, there's 1 or maybe 2 dots, meaning that there's sort of low to at best medium confidence in the sort of evidence for that change. The main reason for this is that, as I was just saying, sort of traditional ways of doing detection and attribution really rely on these global climate models, and for good reason. They're sort of our only tool that we have for sort of doing this experimental exploration of how the Earth system might be changing. But of course, global climate models are just a model, and so they're good at some things and they're not as good at other things. And one of the things that they're not quite as good at is simulating changes in regional precipitation. So when we kind of start to get down to these subcontinental scales, different models sort of simulate wildly different responses to human influence. And kind of when you look across a set of models, it can be really difficult to make conclusive statements here. So that kind of motivates the real, that kind of is the main motivation for what I'll be sharing today, is that can we kind of come at this detection and attribution problem from a slightly different angle, and maybe focus in or base most of our statements here on these measurements or observations of the real world, and kind of see what we can get from that standpoint. So to kind of give a roadmap here for the methods anyway, the first thing, in kind of a new way of approaching this regional detection and attribution problem, the first thing is that we are still going to use global climate models, but we're going to use them in a perfect data sense, or sort of in testbed mode. And we're going to use these to sort of set up a formula for how we can do regional detection and attribution. And again, using them in this testbed mode where we sort of know what's happening, that ensures that we kind of have a good formula that's sort of appropriate for what we're looking at, and make sure we're getting the right answers for the right reasons here. But then we're going to set the climate models aside and kind of focus in on the observational record, the measurements from these weather stations that I was talking about. And for that, we'll need some statistical methods to do this local detection and attribution. Of course, the signal to noise is a challenge when we're using weather station data. So the statistical methods will help there. And again, importantly, I think this gets around this climate model uncertainty problem, which, again, as I said, is undermining sort of more traditional ways of doing detection and attribution, again, specifically for extreme precipitation. And then again, the punchline, as I said at the top, was that when we put these together, they do allow us to get some conclusive statements about what human influence is doing to extreme precipitation events sort of locally here when we zoom in on the United States. So that's where we're going here. So let me spend a little bit of time talking about sort of the framework of how we're setting up doing this observationally based detection and attribution. So again, at a very high level, we've at first proposed sort of a conceptual model for how we might model a time series of extreme precipitation. So we have data over about 120 years here. So T here indicates the year. S indicates a given geospatial location. And just kind of thinking about what components do we need to include in a model for trying to understand how the observed precipitation might be changing over space and time. So on the left-hand side here, this is the input data. This is what I was talking about a moment ago. These are the daily precipitation measurements, and we're actually taking out just again, focusing on daily extremes. We're just looking at the largest measurement that occurs in each year, or we'll actually be looking at different seasons. But that's essentially the main input data for the analysis. When we move to the right-hand side, again, this is kind of our conceptual model for how precipitation might be changing over space and time. The first piece is a pre-industrial average, so this time invariant. And this is designed to represent sort of a background climatology or pre-industrial average. Kind of what do rainfall extremes look like in the absence of any external forcing, human or otherwise. The next piece is an externally forced piece. So this is now trying to get at essentially secular changes over time. This could be, again, externally forced, meaning outside of the sort of the natural Earth system here. So these could be human elements, which I'll say about in a minute here. It could also be natural forcings, things like volcanoes or solar or other things as well. But that's kind of the forced piece. And then everything else essentially is in a bucket that we'll call internal variability, which is, again, all year-to-year changes in rainfall extremes that cannot be described by either the sort of background climatology or some externally forced change. We do actually, one of the novelties here is that we do actually split this into two pieces. So we have this PD term, which is looking at these low frequency drivers. That's trying to characterize the influence of sort of these known modes of climate variability, things like the El Nino Southern Oscillation, other sort of year-to-year sources of variability or oscillations that we know influence rainfall. So that is sort of specifically modeled, but then this weather variability term is essentially a residual error term. That's kind of everything else that we can't account for using these other parts of the equation. So the part that I'm not going to say as much about, there's a very long paper on this if you're interested, or I'd love to answer questions later. But starting with this formula, this is again extremely general, right? Each little piece in this sum could be represented in a number of different ways. And what we did was, again, using a very large volume of data from the CMIP6 archive and others, was to start to pare this down to kind of think about when we're focusing in on the United States over the last 120 years, in what ways can we simplify this and sort of write down something that's much more specific, and but at the same time make sure we're not missing interactions that we should be accounting for or nonlinearities or whatever. We're kind of really taking a very careful step through each of these pieces. So I'm not going to go through all of them, but I do want to say a little bit about the results that we got, or sort of where we ended up for this externally forced component. So again, there's a citation there, which I have a link to at the end of the talk. But what we found, and again, this was using the global climate models in sort of testbed mode, was that for this forced component, we could safely ignore the effect of natural forcing agents. So this would be things like volcanic activity and solar radiation. Now, this does not say that those are not important forcing agents for global climate or for other things, temperature or other things that are not precipitation. But again, very specifically when we're focusing in on one place, that is the continental United States, and a specific time period, the last 120 years, those sort of can be safely ignored. Similarly, we can ignore some human anthropogenic forcing agents. Specifically, we can safely ignore stratospheric ozone and changes to the land surface. However, there are two things that we definitely cannot ignore. It was very clear, kind of a message emerged from the models. Again, and a surprise to no one, but the two things that we do need to account for are greenhouse gas emissions and then anthropogenic aerosols. So these two are kind of the main players, again, when we're talking about changes to extreme precipitation over the United States in the last century. So let me just say a little bit, give a little bit of background to kind of make sure we all know what we're talking about here and kind of what we expect from these pieces. Again, the major player, again, a surprise to no one, is greenhouse gas emissions, and this is kind of the primary anthropogenic forcing that various human activities impose on the Earth system. The way that we would maybe expect this to impact precipitation is as a result of the greenhouse effect, which of course refers to the process of radiation entering the Earth's atmosphere from the sun, warming the Earth's surface, and then being trapped in the atmosphere as well. And there's a few greenhouse gases that we need to take care of. First is carbon dioxide, but also methane, nitrous oxide, and a few others. And of course, human activities enhance this greenhouse effect. And again, that's primarily through burning fossil fuels, but also other ways that happens as well. So greenhouse effect means that the Earth's atmosphere is warmed, and the human activities are sort of enhancing that effect, the idea of global warming. When it comes to precipitation, how we would expect this global warming to impact precipitation is through a very famous Clausius-Clapeyron equation, which again says that as the atmosphere warms by 1 degree, for each degree that the atmosphere warms, we expect extreme precipitation to increase by about 6%. And the increase is because warmer air can hold more water vapor. So when storms are moving around, they can rain out at approximately 6% more per degree of warming. And the radiative forcing from these emissions contribute to what we would call a slow precipitation response, where they have this sort of lagged effect on rainfall. There's sort of a long-term warming of the atmosphere and ocean, again, which sort of on longer time scales would result in these changes to precipitation. So that's greenhouse gas emissions. Again, very well studied and pretty good expectations about what should happen in terms of their relationship to rainfall. Anthropogenic aerosols are a bit of a different story in terms of what we know and what we might expect for precipitation. But again, the air around us as you're breathing right now from wherever you might be is filled with lots of tiny particles and also liquid droplets. And those are what we call aerosols. Globally, a lot of these aerosols are natural in the sense that they're coming from the ocean, from sea salt, dust from desert areas or arid areas, also volcanic ash, smoke from forest fires, and things of that like. But then another large fraction of these do come from human activities that are man-made, and this is again primarily the byproducts of again burning fossil fuels. But also a number of other things. And maybe just at a higher level, you could kind of think of these as air pollution or smog. So that's what's trying to show in this figure here. These obviously have very large impacts on weather and climate. They also have a huge impact on human health. But again, we have a much less, it's much less clear exactly on how they are influencing, especially when we're talking about extreme precipitation. But there are two things that we would expect, that they have sort of these two primary impacts on both the Earth system as a whole, but also rainfall specifically. And the first one is what we would think of as a direct effect, so that as aerosols are emitted from the surface, they enter the atmosphere, and then they interact with the incoming sunlight. So that happens via a reflection or a scattering of solar energy. So actually, if there's more aerosols in the atmosphere, that actually serves to offset global warming in the sense that it's sending off some of the solar energy that's coming in. This direct effect that I've just described here is more or less has a similar effect everywhere, that there's sort of an overall global effect of how many aerosols emissions are in our atmosphere at a given time. The second impact that these would have on the Earth system and also rainfall are, the first one was the indirect effect. The second one here is a more direct effect. Again, as aerosols are emitted, they enter the atmosphere and then they start interacting with clouds, and they impact the rate at which clouds form and also what type of clouds form. So again, this you could think has a very large impact on rainfall. Whereas that indirect effect is a global thing, this is a much more localized thing, that it depends much more on how close you are to a given emission source. Again, so we when we talk about this aerosol effect, we actually have these two effects that we need to think about when again on extreme precipitation. The first is this slow response, which comes from reduced radiative forcing. So similar to greenhouse gas emissions or warming the atmosphere, which on longer timescales increases rainfall. As aerosols are cooling the atmosphere, reducing the radiative forcing, which again leads to on longer timescales this slow precipitation response. But there is also this fast precipitation response that comes from, again, altering cloud properties that again happens on much shorter timescales. So again, kind of coming back to this force piece, I remember we said there were these two things that we had to worry about. The last thing that we were able to show is that this sort of additive or this linear framework is also appropriate for characterizing this forced response here. So, and again, this is kind of how we're going to ultimately do the attribution exercise here. So in this approximate formula, these betas, the beta slow and the fast, are what we'll call the local attribution coefficients. And these, again, simply describe the magnitude and the sign of the response, whether these forcings are increasing or decreasing rainfall and to what extent. The forcing, the Fs, the capital Fs up here on the right-hand side are actually going to be a fixed forcing time series. And this is what I'm plotting here at the bottom. So again, we have a greenhouse gas forcing time series, this global aerosol radiative response time series, and then we have a local aerosol piece over here. And just to kind of step through these, and I guess, well, before I do that, these are observational quantities in the sense that they're reconstructed. So we have pretty good sense of what the greenhouse gas emissions have been over the last several hundred years. And similarly for these other things, we have pretty good data sources here for these. But the radiative forcing from greenhouse gas emissions shown here on the far left. The different colors represent the different greenhouse gases. So again, carbon dioxide, the orange bar here on the bottom, if you can see that, is kind of the main player, but certainly methane and other things are contributing there as well. And again, the numbers are all positive here. So this is an increase or a positive radiative forcing. When we go to the middle here, this is a reconstruction of the effective radiative forcing from aerosols, kind of globally on the global scale. And you can kind of see how that trajectory is going. It was, getting stronger over the first 70 years and then sort of starting to come back towards zero. Again, this is a negative. These are all negative numbers here. So again, that refers to a reduction in the radiative forcing. And then when we come back to this fast response or this local effect of aerosols, there's actually quite a bit of work in this methodological paper I was just talking about that where we worked very hard to figure out a good way to characterize these, since this is, as you might imagine, pretty complicated. And what we came up with was that we can actually represent this response by using these emissions data, the sulfur dioxide emissions, again, which are reconstructed from observations. These are what get fed into global climate models as boundary conditions and so on. And again, sulfur dioxide is sort of one of the major players in aerosols. It's a precursor to a lot of the aerosol emissions that we think of. And again, the trajectory here is kind of those emissions were increasing over the first 60 or 70 years, but then in the mid 1960s and 70s, when the EPA was introducing its clean air standards, those have really dropped off these emissions to quite low levels of where they are today. Okay, say just one or two slides here on the methods. Again, would be more than happy to chat about this later or offline. But the two sort of methodological pieces that we have here are a sort of spatial extremes analysis, and then kind of a hypothesis testing, significance testing exercise for the attribution piece here. So I didn't say too much about it other than the forced piece, but we derived a specific DNA formula, kind of different parts of it as described. I apply that within sort of a GEV regression framework to each station, and then use Gaussian processes to do some spatial modeling of those coefficients, again, which is really useful for sort of the signal to noise considerations here. And then we're quantifying uncertainty in this first part using bootstrap or non-parametric bootstrap methods. Once we've done that, though, we do want to take this a step farther and kind of look at significance testing. So for the actual detection and attribution, we use, again, resampling methods to define null distributions. And also, since we're looking at sort of a spatial distribution of tests, when we look at these things locally, we have a multiple testing adjustment to make sure that we're not overconfident in our results. And the ultimate goal here essentially is to assess both the spatial patterns of change, or how human influence is affecting rainfall sort of with maps and spatial patterns. But then we also want to come back to this time to emergence question to see if we can identify when these different forcing agents sort of have a significant impact on rainfall. And I hinted at this earlier, but we're actually going to apply this whole framework separately for each 3-month season. So wintertime, spring, summer, and autumn. And the reason we're doing that, really, that especially for extreme precipitation, different mechanisms, different weather phenomena tend to lead to extreme precipitation events in different parts of the year. In the wintertime here in the United States, these tend to be sort of large-scale atmospheric events. In the summertime, if you live in the Midwest, you have a lot of convective precipitation, thunderstorms. In the late summer and fall, hurricanes are tropical cyclones are a big player. So anyway, kind of looking at different parts of the year separately allows us to account for these different mechanisms, and also get at the fact that potentially these anthropogenic forcing agents are impacting the different types of precipitation events in different ways. So that's, I guess, the extent of the methods that I wanted to talk about. So let's get on to some results here. Okay, so the first result here has to do with sort of the spatial scales of attribution. As I've kind of hinted at a few times here now, detection and attribution is, of course, a signal-to-noise exercise. And we try to identify a change to the Earth system, some aspect of the climate system, but then we need to see if that signal is sort of large relative to the noise or the uncertainty. And of course, the easiest way to reduce noise is sort of in a large data sense, is to average over larger areas, and that will kind of bring the noise down. But again, of course, we don't want to average over too large of an area, because we want to maintain these local conclusions so we can kind of show what's happening at sort of impact relevant scales. So what we did, the first thing we kind of looked at was how, at what spatial scales can we detect and then attribute the human influence to these different forcing agents. And for this, we sort of considered a set of what I'll call attribution regions, where we start with the entire US, and then we start subdividing it down. So we split it into 2, and then 4, and 13, and 75, and so on, all the way down to individual little grid boxes, little 25-kilometer square grid boxes. And we want to kind of see, what are these spatial scales? Where can we detect a human influence? Where can we not? And kind of what might be leading to that. And so here's this first results figure to show you, kind of looking again at the spatial scales. So there's a lot going on in this plot. Let me try to walk you through it here. So the different columns here represent the different 3-month seasons. So DJF, that's December, January, February, wintertime, March, April, May, or spring, June, July, August, or summer, and then September, October, November, and autumn. And the top row here is looking at the slow precipitation response, which is, again, coming from both the greenhouse gas emissions as well as the sort of global aerosol effect. And on the bottom row of these panels is the fast precipitation response. It's in this local aerosol response here. As you move from top to bottom on this figure, we're looking at sort of decreasing the spatial scale. So we start where we just have one region where we're looking at the entire CONUS, and then we divide it into 2, 4, and so on. And then on the x-axis here, we have the sort of fraction of the US where we have a significant attribution conclusion. And finally, the color indicates, is that leading to increases or decreases. So if we kind of, zoom out as far as possible here, looking at the entire US, that would be the top little row of each of these panels. we can see that there are significant attribution conclusions for both the fast and the slow response, stronger for the slow response across all the seasons. And as we move to smaller spatial scales, again, as we would expect, the strength of that signal does decay, that you have sort of less and less of the US that you're able to say has a significant attribution response here. But at least for the slow response on the top here, we do have some areas where we can identify with a moderate level of significance a human influence on these very small scales. So that would be at individual grid boxes. So that was really exciting, that we can even for these very localized scales, we can kind of still say something meaningful about the human influence. So let's start there. Let's go right down to those individual grid boxes. Since we have some significance at those levels, let's see what those patterns look like. So again, a slightly complicated figure here, but again, the rows now represent the different seasons: winter, spring, summer, fall. And the columns now of these maps look at the fast aerosol response, the slow aerosol response, and the slow greenhouse gas response on precipitation. And hatching now indicates where these conclusions are significant, so with either a moderate or a strong level of significance. And then the color again indicates which direction things are moving here. So green are places where extreme events are larger for larger values of that forcing agent, and brown's the other way around. So as we kind of step through this, maybe focus on the greenhouse gas column first here on the right side. Again, the dominant color here is green. So again, that means as greenhouse gas forcing is increasing, as it has been over all of the 20th century, rainfall will also be increasing. And that, again, is exactly what we would expect from that Clausius-Clapeyron equation that says that rainfall increases by 6% per degree of warming. And kind of looking at the limits of this color bar, again, remember, we're talking here about daily precipitation extremes. So that means for the largest precipitation total in a season, that is now increased by as much as 10 millimeters in some places. That's kind of the magnitude of the response here. And again, we do have a lot of places that are statistically significant. That's just indicated by the hatching. It is true, however, sometimes, and in some cases, the opposite happens, that you have these brown areas where actually the greenhouse gas forcing leads to decreases in precipitation. So that kind of reiterates, I think, the importance of looking at things locally. That if you're a water manager in the Southwest, for example, you might need to know what's happening specifically in your area as opposed to what's happening sort of for the US as a whole. If we look at the middle column here, if we kind of think about the long-term effect of aerosols, again, the main color here that we see is brown. So again, that means as that slow aerosol forcing is getting stronger, precipitation will be decreasing. So that's, again, what we would expect. But however, I guess I should point out that the sign of the middle and the right column are opposite by construction. So you kind of have this offsetting thing going on here. When we get to the short-term impact of aerosols, this fast response over here, again, I think the main message is there's no longer a dominant color. That in some places you have where the greens are showing up, you have that as this, as the browns, as this forcing agent increases, precipitation decreases. That's kind of showing up maybe more in the wintertime and in the spring. But in many other places, you have greens over here, which means that as the aerosol emissions increase locally, the fast precipitation response is that rainfall also increases. There is, of course, a strong seasonal dependence. The maps look very different in different parts of the year. But I guess this was kind of a headline message that we spent a long time trying to make sure we had gotten correct, because this is sort of the first, or one of the first observational evidence for aerosols, these local aerosols increasing rainfall through what's sometimes referred to as convective invigoration. And this, again, has been identified in modeling studies, but it's less so on the observational side of things. So that was exciting. Okay, so the last result that I want to share here has to do with this time to emergence question. So again, these maps that I was just showing you were kind of aggregating over time, looking at sort of what's the largest effect of each of these forcing agents. If instead we want to think about sort of emergence, of how these things were evolving in real time, we can look at the trajectories, the precipitation response trajectory of each of these forcing agents. For now, we're going to average over the US just to kind of simplify the presentation, but the next slide, then I'll show you kind of how things look more locally. And the key question here really is, when do these individual signals, the slow aerosols, slow greenhouse gas, fast aerosol, when do those signals emerge from baseline conditions? But then in addition to looking at each of those individually, we can also look at the sort of the sum total anthropogenic signal, where we can add them all up to kind of get a sense of what are the overall trends in precipitation. Essentially, if you'd been standing on the ground in one place for about 120 years, what would rainfall trends have looked like for that area? So that's this sum total anthropogenic signal. And again, starting at the CONUS scale, so we're averaging over the whole United States. Again, I'm showing results here for each season, winter, spring, summer, fall. The colored lines show these sort of isolated effect of each of these forcing agents, the slow greenhouse gas response in the red, the slow response from aerosols in blue, and then the fast aerosol response in green, as well as the sum of those things is the black line. But then I've also put on here these dashed vertical lines, which show the first time that the uncertainty bar there on these trajectories departs from zero and does not go back down to zero. So the red line shows the first year in which that isolated greenhouse gas signal emerges from zero. And same for the black dashed line. That's where the sum total or combined anthropogenic signal emerges from zero. And wintertime, maybe something else happening, but in the other three seasons, we're having a very interesting result, which is that the greenhouse gas signal, that red dashed line, emerges before the combined anthropogenic signal. So that, if you're looking at just the black curve, you might not be able to detect any changes, but when we can pick them apart, we can see that the greenhouse gas signal actually emerged quite a bit earlier than might have been thought otherwise. What that also implies is that there's sort of this masking thing happening from the aerosol, that the other two, that the slow aerosol and the fast aerosol response are sort of offsetting those expected increase to greenhouse gas emissions, so that they're kind of masking the effect of greenhouse gases on the overall anthropogenic signal. So again, we expected human influence to lead to increases in rainfall, and I guess what I'm showing here is that is true. That at least some of the anthropogenic effects through the greenhouse gas forcing do lead to increases, but some of that increase has been offset or masked by these aerosol sources. And as we kind of move to smaller spatial scales, I wanted to kind of look at the same quantity, but again aggregated over these smaller regions. So again, I was trying to make essentially a version of these time series, but for each different spatial region that we might be interested in. And here's my attempt to do that. So again, we have the different seasons, and then the 4 rows here are the different spatial scales. The plotted color here represents the anthropogenic emergence time minus the greenhouse gas emergence time. So we take what year the black line, what year that signal emerges, and subtract off the year that the red line emerges. So that green is places here where that greenhouse gas signal emerged before the combined anthropogenic signal. So that means these are places where the greenhouse gas signal was masked or kind of disguised by aerosols. And we do still have this, that we do have greens here, sort of the significant effect showing up at these smallest subregions that I've shown here, which are about 100,000 square kilometers. And of course, there are a few other, there's one other color showing up here, which is the purple, which if you can read that here, that's times when only the anthropogenic signal emerged. So that's kind of like what happened in wintertime back here, that the greenhouse gas signal never quite got above zero, even though the sort of combined anthropogenic signal did. So that happens, but I plotted the year in which that happens. That when that does happen, it happens really late in the record, in the last 10 or 15 years or so. So that's kind of what we can say about the emergence of these individual signals. The last thing I'll say before I wrap up here is just some implications of this work, I think, for natural hazard risk. So again, kind of at high level, think about what we've shown is that these increases that we would have expected from greenhouse gas forcing have been offset by aerosol emissions, at least up through the 1970s. However, in the last 50 years or so, this masking effect has gradually gone away. If you can remember back to that little trajectory of well, I guess I'll just run back there real quick. That aerosols were increasing much like, oh, maybe I shouldn't have come back. Here we go. That aerosol emissions were increasing, marching upwards, much like greenhouse gas emissions were, until this sort of policy change when they were sort of turned off. So they kind of dropped off very sharply. Sorry, let me jump back to where I was. Maybe a bad idea. So again, we have these two players. One is causing rainfall to increase. The other is sort of causing rainfall to decrease. But over the last 50 years, that thing that's causing rainfall to decrease has essentially been turned off. So what that means, I think, is that we could expect the greenhouse gas signal to dominate recent and sort of near future changes in precipitation. And this actually kind of interestingly, completely independently verifies some other results that have come out in the last year or two that are talking about how human influence is increasing the risk of flooding, both sort of from natural variability, influencing natural variability, as well as this masking thing that we were talking about. And again, if you go back to summer of 2022, there were these 5 unprecedented flooding events in the U.S. There were these 5 1,000-year storms that all happened in the course of a few weeks that caused crazy flooding. There was these catastrophic events in Pakistan, and again, we could probably pick out examples from the last year as well. But just kind of say what this results suggest for changes to flood risk. Okay, that's it. I'll put the takeaways up here again. Here's my email address, and then down here, if you're interested in reading more, there's some DOIs here for. The first one here is those perfect data tests that we use to derive this DNA formula. And we did just have this work was just published earlier this year on the second half of the talk here, the scientific results, if you're interested in reading more. But that's all. Thank you very much.
Excellent. Thank you so much, Mark.